Another example for us that we can explore would be, let's say we want to reduce the power loss in our system and in our shunt. And if you remember, we had our 1 watt power loss target, but let's say now we want to go half a watt. And I hit the enter. Oh, we do have a problem here. Let me fix this. Let me just go 0 for that and okay, half a watt. And as you can see, it's just giving us error. As soon as you do that, it gives us an error, and you can click on OK, and it will automatically open the product selector again. This time, it is recommending a higher gain option device, around 200 gain, as you can see, compared to 100 gain in a previous recommendation, which kind of makes sense because if you want to measure the same current but you don't want to spend as much shunt power, you generally need more gain, and that is what it's kind of showing you. So we cut the power by half, and we are multiplying gain by 2. And let's just, for example, pick again 2167 here. And as you can see, doing that and increasing gain, it is going to throw off your boundary condition all of a sudden. The boundary condition was between 5 to 0 volt. Right now, you're going up to 8 volt plus. So you're basically clipping. To fix that, similar to last time, we can reduce the shunt resistance further, going from 2 milliohm down to 1 milliohm. And let's see how that affects our output. And if you go see output, now it is fitting well. That brings back the output within a boundary condition. And let's say that we are happy with this. And but however, if you look at this and if you scroll up, with the recent modifications that you implemented, which means you cut the power by half, increase the gain, and then you reduce the shunt resistance to fit your boundary conditions, you'll see that the best full scale accuracy that you can achieve is going to now be 2% plus, 2.446% right now. And this example really shows the fundamental trade-off between shunt power and accuracy. With this specific device, in this case, once we push for lower shunt power, accuracy becomes a limiting factor. There is only so far you can go before you hit the performance ceiling of this particular amplifier, and this is what you are seeing here. At this point, the next step is exactly what we've been talking about throughout this demo. You can go back, try different amplifier, continue iterating, and by exploring different devices, gain shunt values, you can again converge to the solution that is acceptable for your system and for your application. And that is where this tool really shines. It lets you see this trade-off clearly and quickly without having to do any math manually yourself. Now, let's take a look at the plots at the bottom of this page, error plots. Take a closer look at these, which these plots kind of show the system's overall error budget and accuracy, basically. You notice that the tool displays two different error curves here. We have two different kinds. The first one on the right is a percent error versus load current. This is the industry standard way of communicating current sense accuracy, and it is a very useful at the mid load or full load condition, mid or full load conditions. However, this plot can be misleading near the zero current condition. This is zero current area, and that is because, as you can see, at zero current condition, we are essentially dividing by 0, which create asymptotes here. And the curve shoots off toward infinity, and it becomes impossible to understand what actually happening there, what kind of accuracy we have at or near 0 amp. That is exactly why we included a second plot right next to this plot. And the second plot on the left shows the actual current error in the amp versus load current, not the percentage error anymore. By expressing the error directly in amps, this plot avoids the division by zero problem and clearly shows how much current error or resolution window you have at each operating point. Again, this plot is especially helpful at a very low or zero currents. Here, as you can see, you don't have asymptotes anymore. You have an actual number that you can refer to. And you typically see that at 0 amp, the error is dominated by input offset. As the load increases, the other contributors like a gain error, resistor tolerance start to matter more, and they kind of add to your overall error amount, and error band basically widens as we move forward. And when you look at the both plots together, you get a much clearer real-world picture of accuracy across the entire operating range. And we wanted to offer both of them to you, whether so that you can have an understanding of the accuracy level, whether in a zero load current or full load current. One plot tells you again how the system behaves in terms of industry standard accuracy specs, and other plot tells you what actually means in amps, where it matters most in practice. Another handy feature of this tool is, as we mentioned earlier, it has an export and import functionality and capability, and we have buttons here at the top for it. You can easily export your setup and save it for later analysis, or import the previous configuration and pick up right where you left off. We also have this import button in the first page as well, where you can open up an existing setup from a previous work. And we also have at the top a design summary tab section, which is basically this tool's final deliverable view. It pulls everything you entered and selected in one place. You can review, share, document this, and specifically consolidate the system specification, shunt characteristics, the amplifier you selected, its details, schematic references, and error curves and performance results. It is also formatted for clean export and printing. With that, we conclude our current sense amplifier design tool demonstration. Please make sure to visit our website and to use this great tool, and let Onsemi team know if you have any comments or questions. Thank you very much.